Hello, my name is Ryan Chazen. I am a student in Math 32, Section 8D at the University of California, Merced, and I'm taking this class in fall 2020. Today I will be discussing the topic of gamma distribution. So what is the gamma distribution? The gamma distribution is very similar to the exponential distribution. So they are both used to measure the wait time before an event. But what is the difference between the exponential and the gamma distributions? Exponential distributions are used to measure the time before the first event, whereas the gamma distribution is used to measure the time before a certain event, the kth event. So there can be multiple events, and the gamma distribution can be used to measure any of them for the time before. So here's the textbook definition slash equation for the probability density function of the gamma distribution. So a continuous random variable has a gamma distribution with parameters alpha is greater than 0 and lambda is greater than 0. If its probability density function f is given by f of x equals 0 for x is less than 0 and f of x, and here's the equation here, for x is greater than 0, where the quantity gamma of alpha is a normalizing constant such that f integrates to 1, we denote this distribution by gam with the parameters alpha, comma, lambda. And also here is the CDF equation, which is the cumulative distribution function. All right, so I know that the equations can look a little confusing, so we'll go through an example problem. So engineers designing the next generation of space shuttles plan to include two fuel pumps, one active, the other in reserve. If the primary pump malfunctions, the second is automatically brought online. Suppose a typical mission is expected to require that fuel be pumped for at most 50 hours. According to the manufacturer's specifications, pumps are expected to fail once every 100 hours. What are the chances that such a fuel pump system would not remain functioning for the full 50 hours? We are given that lambda, the average number of failures in a 100-hour interval, is 1. This means that theta, the mean waiting time until the first failure, is 1 over lambda, or 100 hours. Knowing that, let y denote the time elapsed until alpha equals the second pump breaks down, sorry. Anyways, our PDF, here it is, the 1 over 100 squared gamma 2, e to the negative y over 100 times y to the 2 minus 1. So we can simplify that down a little bit and we get this. So the probability that the system fails to last for 50 hours is the probability of y is less than 50 equals the integral from 0 to 50, because it's 0 to 50 hours, of 1 over 10,000 ye to the negative y over 100 dy. So we solve this integral by using integration by parts, and we get 0.09. So therefore, the chances that such a fuel pump system would not remain functioning for the full 50 hours is 9%. So hopefully that example clarified a little bit about what the gamma distribution is. And so how do we use the gamma distribution in the real world? So gamma distributions, as I mentioned earlier, are good for waiting time modeling. So will the bus come in the next 10 minutes or the next 60 minutes? That's an example of how you'd use that. The gamma distributions are also good for reliability, like such as failure modeling. An example would be the fuel pump problem that I just gave on the last slides. And the gamma distributions are also good for service time modeling. So an example of this would be, how long does it take for a McDonald's cook to make a Big Mac? Here are the sources that I used in this video presentation today. And I hope that you enjoyed it. Thank you so much. Have a great day.